Dear students, welcome to Basic Thermodynamics video lectures. So in this video lecture, we are learning about Unit 2. The title of Unit 2 is First Law of Thermodynamics. So these are the contents of your Unit 2. So here we are defining First Law of Thermodynamics, then related Joule's experiment we are learning, then corollaries, PMM1, Perpetual Motion Machine Kind 1, then first law applied to non-flow processes and first law applied to flow, that is open systems we are learning, then related problems we are calculating. We are so closed system and open system first law we are applying, related thermodynamic analysis we are doing in this particular session. Okay, then coming to the definition of first law of thermodynamics. So, as we know that the laws of thermodynamics are natural hypotheses based on observation of the world in which we live. So, it is observed that heat and work are two mutually convertible forms of energy, and this is the basis of first law of thermodynamics. Then, the first law of thermodynamics is a law of conservation of energy, which states that energy neither be created nor destroyed, it always conserved. Okay, so however it can change from one kind to another. Even the other way also we can able to define this: the total energy of an isolated system, so wherein mass is constant as well as energy is constant, so in all its forms remain constant. Then another way, all the energy that goes into a system comes out in some other form. Okay, simply we can say that energy is always conserved. Okay, energy does not vanish and has ability to be converted into any other form of energy. Then no machine can produce energy without corresponding expenditure of energy. Energy cannot appear from nothing, nor can it convert into nothing. Okay, so many ways we can able to understand the first law of thermodynamics, but ultimately the meaning of all these particular four statements are same. Then coming to the terminology what we are using in the first law of thermodynamics. Okay, so first of all, let us understand what is the meaning of energy. So this is not new term to you. Already the mechanics we have introduced. Anyhow, thermodynamics perspective, how do we define energy? So energy is nothing but capacity of a substance to do work, but this energy cannot be seen, but it can be felt by change of properties of the system. Then broadly, energy can be classified as stored energy and transient energy. Stored energy is nothing but energy contained within the system boundaries. Okay, that is called the stored energy. Examples are potential energy, kinetic energy, internal energy, etc. Okay, many more we have, but for thermodynamic analysis, so these three energies we are focusing our attention. Then coming to the transient energy, which crosses the system boundary. Examples are heat energy, work energy, electrical energy, etc. But for our thermodynamic analysis, we are concentrating on heat energy and work energy. Then what is internal energy? It is also called stored energy, generally which is represented with the letter U. Okay, so internal energy is nothing but sum of all microscopic forms of energy of a system. So it is related to the molecular structure and degree of molecular activity. And here in this figure we can observe various forms of microscopic energies that make up sensible energy: molecular translation, molecular rotation, electron translation, so molecular vibration, electron spin, nuclear spin. So depending upon given application appropriately, so that motion we are selecting, that microscopic form activity we are selecting. Then Joule's law, okay, which is related to the internal energy. So what Joule's law states, the internal energy of a perfect gas is a function of absolute temperature only. Okay, U is equal to F of T. Okay, so generally the internal energy is represented by the symbol capital U. The change in internal energy in a process is represented as delta U, which is nothing but U2 minus U1. The specific internal energy, That means the internal energy dividing with the unit mass, we can able to call it as a specific internal energy. So generally that we are representing with lowercase u or u bar. So which depends upon whether it is expressed on unit mass or per unit mole basis. Okay, then the change in internal total energy of a system, so E2 minus E1 is equal to, so change in kinetic energy plus change in potential energy plus change in internal energy. So this way we can able to. Okay, so depending upon the system what they are giving in the problem, whether it is a closed system or open system, okay, accordingly, so the relation you have to consider. Okay, then if energy is stored in a gas, if a certain amount of heat is supplied to a gas, the result is that temperature of gas may increase or volume of gas may increase, thereby doing some external work. Or both temperature as well as volume may increase. But it will be decided by the conditions under which the gas is supplied heat. Okay, so if during heat of gas the temperature increases, its internal energy will also increases. Okay, then coming to the another important parameter we consider in the thermodynamic analysis is nothing but the enthalpy, that we are representing with capital H or lowercase h. Lowercase h for stands for the specific properties, specific enthalpy. Okay, per unit mass basis you are considering, then lowercase enthalpy, I mean h you are selecting. Okay, so you are using, then here enthalpy is nothing but the total heat content of a system we can able to represent in the form of a enthalpy. Then this is one of the fundamental quantities, so which use in thermodynamics, so which is nothing but sum of internal energy plus pressure volume product. Okay, mathematically we can write it as h is equal to u plus pv. Okay, so enthalpy of a fluid is a property of fluid since it consists of sum of property and product of two properties. Since enthalpy is a property like internal energy, pressure, specific volume and temperature, so it can be introduced into any problem whether the process is a flow, that is a open system, or non-flow. Non-flow is nothing but the closed system. Then total enthalpy of a given mass m of a fluid can be represented as capital H is equal to capital U plus PV. Okay, then Joule's experiment, Joule's paddle wheel experiment. Okay, so this particular experiment easily we can able to understand through this particular video. Okay, so generally the Joule's experiment which we are using to determine the mechanical equivalent heat. So here we have a rigid well insulated container. Okay, so wherein a known mass of water is taken here, the blue color shaded area. Okay, then the container is provided with a paddle wheel. Here we have a paddle wheel here. Okay, so the insulation is provided to prevent any heat interaction. This is well insulated container, so to prevent heat interaction with the surroundings. Now the water, okay, so is stirred by the paddle wheel which is driven by allowing a known mass connected to a paddle wheel by means of cards, these are the cards. Okay, so negligible mass and frictionless pulley we have to fall through a specific height h, lowercase h. Okay, the work transferred to the water system is calculated in terms of decrease in potential energy of falling mass, so delta PE is equal to mgh. Okay, so due to this particular work interaction, the temperature of water increases. So the change in internal energy of water system is computed from the rise in temperature and heat capacity of the water in the container using the formula Q is equal to mc delta T. Okay, so like that the Joule conducted many number of experiments involving different types of work interactions and found that the work expended was proportional to increase in thermal energy, that is Q is proportional to W. Okay, so this in other way we can able to see here this cut view, if you see sectional view. Okay, so here again the same container, insulated container which is filled with the fluid and a thermometer is placed, and so here rise and falling of this particular known mass of weight. Okay, so decrease of potential energy leads to increase in the internal energy. Okay, so this here it is given from the Joule's experiment, Q is equal to W or Q is equal to JW, the constant of proportionality J. okay, which is nothing but the joules equivalent or mechanical equivalent of heat. Okay, so in SI is system of units, both and the heat work are measured in joules, and as such the proportionality constant J takes a unit value. Okay, then from the Joule's experiment, the same process if you represent on the XY diagram, wherein any properties. So generally here, distance to temperature we can able to take, or any known properties on x-axis and y-axis if you have considered, and say here number one is the initial condition of the system and two is the final condition of the system. Okay, then it is undergoing a so initial path like this, and again it is returning back to the final path, so it is forming a cycle. So cycle completed by a system with two energy interactions. So here adiabatic work transfer W1 to 2, and which is followed by the heat transfer 2 to 1. Okay, so in the given simple example, so there are two energy heat transfer quantities as the system performs a thermodynamic cycle. So if the cycle involves many more heat quantities, the same results will be found, and which can be expressed algebraically. Delta W cycle is equal to J of delta Q cycle. Okay, so where J is a Joule's equivalent, and this can be expressed in the form of a cyclic integral dW is equal to J of cyclic integral dQ. Then in this manner we can express, and where this particular symbol denotes the cyclic integral for a closed path. Okay, then the first law applied to closed system in general way. Okay, so here the figure 2.02, if you observe, we have taken a system, so wherein in this particular system only single heat interaction and work interaction. Okay, so for this particular system how do we apply the first law of thermodynamics? Okay, then in the figure if you observe, here we have taken another system. The system consists of many number of components, suppose like refrigerator you take. So the refrigerator consists of what are the four principal components: compressor, condenser, expansion device, and your evaporator. Okay, so wherein there are different interactions and work interactions taken place. So refrigerator as a system you have taken, many more components you can get. Okay, then for that a separate equation we will get. Okay, now here if you observe the expression, the sigma W cycle is equal to sigma Q cycle applies only to systems undergoing cycles, and algebraic summation of all energy transfers across the system boundaries is zero. Okay, but if a system undergoes a change of state during which both heat transfer and work transfer are involved, the net energy transfer will be stored or accumulated within the system. Okay, so if Q is the amount of heat transferred to the system and W is the amount of work transferred from the system during the process as shown in the figure 2.0, the net energy transfer Q minus W will be stored within the system. Okay, so the energy stored is neither heat nor work, and it is given a name called internal energy. Earlier I have explained that. Okay, or simply energy of the system we can call, and this can be mathematically expressed as Q minus W is equal to delta E, where delta E is increase in energy of the system, Q is equal to delta E plus W. Okay, so if there are more energy quantities like your refrigerator, air conditioning system, or some other your steam turbine plant you have taken. Okay, so then in such case, then we know already while learning about in the first unit heat and work. Okay, wherein sign conventions we have learned, is it not? Work output is positive, work input is negative. Okay, heat absorbed is positive, heat rejection is negative. So knowing that particular interactions, okay, within the system components, then accordingly if you write expression for the figure 2.1, so this expression we will get. Okay, then another important topic is energy is a property of a system. Okay, so here consider a system which changes its state from state 1 to state 2 by following the path A, and returning from 2 to state 2 to 1 by following path B. Okay, now here the system is undergoing a cycle. Then writing the first law for path A, QA is equal to delta EA plus WA. Similarly for path B, QB is equal to delta EB plus WB. Okay, so the processes A and B together constitute a cycle for which we can able to write sigma W is equal to sigma Q. Okay, then WA plus WB is equal to QA plus QB. Then QA minus WA is equal to WB minus QB. Okay, so from the equations 2.3, okay, and 2.4 and 2.5, which yields that delta EA is equal to minus delta EB. Similarly, had the system returned from 2 to state 1 by following the path C instead of path B, same expression we will get, but here the subscripts changes. Okay, so finally, it is seen that the change in energy between the two states of a system is same. Whatever path of the system may follow is undergoing that change of state. But if some arbitrary value of energy is assigned to state 2, the value of energy at state 1 is fixed, independent of path of the system follows. Okay, therefore, energy has a definite value for every state of system. Hence, so energy is a point function. Okay, then problems related to the Joule's experiment. So here one example we have taken a closed insulated vessel containing 200 kg of water, a paddle wheel immersed in the water driven at 400 revolutions per minute with an average torque of 500 Newton meter. The test run is made for 30 minutes. Determine rise in temperature of water. Okay, so take specific heat of water is equal to 4.186 kilojoules per kg Kelvin. Then here before solving the problem, just write the given data along with its notation. So mass of water m is equal to 200 kg, given number of revolutions per minute 400, and torque t is equal to 500 Newton meter, and test run time t is equal to 30 minutes. Then total number of revolutions made by the paddle wheel, so n is equal to 400 into 30. Okay, 30 minutes for test run we have taken for 30 minutes, 12,000 we will get work supplied to the water 2 pi nt. Okay, then which is a 37,618 10 to the power 3 Newton meter or joules we are getting. Then this work will get transferred to heat, which will result in raising the temperature of water. Okay, so therefore comparing that particular, writing the expression, then unknown we can able to calculate. So rise in temperature of water, how much we are getting, 45 degrees Celsius. Okay, then problems related to the first law for a cyclic process. So this is another variety. Okay, so here a system undergoes a cycle composed of four processes. The heat transfer in each process are 400 kilojoules minus 365 kilojoules minus 200 kilojoules and 250 kilojoules. The respective work transfers also given. Is the data consistent with the first law of thermodynamics? Okay, so we know the first law of thermodynamics, which is a law of conservation of energy. So cyclic integral of delta Q is equal to cyclic integral of delta W. Okay, so calculating that, okay, if both are getting same, then we can conclude that the given data conforms the first law of thermodynamics. Okay, so like that, number of problems we have. Okay, so here also the working fluid in a engine executes a cyclic process and two work interactions are involved. Okay, the working cycle also involves three heat transfer, two of which are given. Okay, then determine the magnitude and direction of third heat interaction. So same law of conservation of energy mathematical expression we can use, and unknown we can able to determine. Okay, so here the negative sign you are getting, which indicates that heat flows out of the system. Then coming to the corollaries of first law of thermodynamics. What is the first corollary? So which is for a process, how do we define when a system executes a process? The net heat interaction equal to the net work interaction plus change in internal energy, which is also called the stored energy, and del q is equal to del w plus dE. Very important expression. Okay, then corollary 2 is first law for an isolated system. Okay, for an isolated system both heat and work interactions are absent, that we know. Okay, in such case delta q is equal to 0, delta w is equal to 0. Finally what remains, dE is equal to 0 or E is equal to constant. Then corollary 3 is PMM1, that is perpetual motion machine, a first kind, so which produces work without the input energy. Okay, so in elaborate we will learn the perpetual motion machine kind 1. Okay, how do we define perpetual motion machine? A first kind is an imaginary device, a hypothetical device, okay, which produces a continuously supply of work without absorbing any energy from the surroundings or from the other systems. Okay, so there is no such mission which could continuously supply the mechanical work without some form of energy disappearing simultaneously. Okay, so such a machine is called a fictitious mission. Okay, so that machine is called what? A perpetual motion machine of first kind. Okay, even we have the converse of the above statement is also true. There can be no machine which continuously consume work without some other form of energy appearing simultaneously. Okay, so there is both statements. So with the help of block diagrams, easily we can able to understand. For example, here any heat engine you consider, which may be a steam turbine or a gas turbine or your internal combustion engine, whatever may be the heat engine you are considering. Okay, so without supplying any thermal energy to the system, work output we cannot able to obtain. Okay, but here in the perpetual motion machine kind one, what it is saying, okay, so without absorbing any form of energy which can able to supply the work continuously, okay, that is not possible, it is mission impossible. Okay, then converse of pmm1 easily we can able to understand with this particular figure 2.5. Okay, any mission you can take. Okay, now here the work you are supplying to the system continuously, which consumes the work continuously, but other form of energy is not appearing. Okay, some heat may be there, okay, that it is not appearing. So even this is also not possible. Okay, then here these are the different models. Okay, enthusiastic engineers they have developed, but initial thrust we are giving, but which could able to run, but the magnitude of work what we are obtaining is not up to the mark. Okay, so these fictitious missions are called what? Perpetual motion mission kind one. Okay, then first law applied to the closure systems. So this is the next topic in our unit 2. Okay, so here six fundamental thermodynamic processes we have. Individually we will learn about it. So the first one is what? Isochoric process, which is also called constant volume process, so which can be represented as V is equal to constant. Okay, then this particular constant volume process, with the help of this particular figure we can able to understand. Let us take a container is filled with a fluid. Okay, and this particular fluid boundary is within the system, I'm saying, okay, controlled by the piston. Okay, but whatever may be the heat energy are supplying to the gas, but the piston movement is here arrested. Okay, fixed position. Okay, so volume remains constant, only pressure variation may be there. Okay, of course, if you are supplying some amount of energy to the system, obviously the properties of system may be changed. But here, as per our assumed condition, volume remains constant. Here the pressure rise, maybe temperature rise. Okay, so this on the PV diagram, how do you represent? See here, on the x-axis we have taken volume, on the y-axis we have taken pressure. Okay, so the constant volume process on the PV diagram, it is a vertical upward. For this particular case, it is a vertical upward direction, process 1 to 2. So V1 is equal to V2. Okay, so here in the isochoric process, the same here with this particular video we can able to understand. We have taken a stove and we have taken a beaker. So here piston we have taken, the piston moment we have arrested, fixed. Okay, see here, observe, if you observe, it is fitted with a pressure gauge and a temperature. As you supply the heat energy, the pressure and temperature is changing but volume remains constant. Isovolumetric process, isochoric process we can call, constant volume process we can call. Okay, then consider the mass of working substance is unity. Okay, suppose 1 kg we have considered. Applying the first law of thermodynamics to the process, Q is equal to what we have learned. Q is equal to W plus delta U. That is Q is equal to U2 minus U1 plus W. Then the work done, W is equal to integral 1 to 2 PdV, which is equal to 0. Is it not? V1 is equal to V2 and hence dV is equal to 0. Then Q is equal to U2 minus U1, then which can be expressed as CV of T2 minus C1, I mean T1. Okay, so for M, for mass of M, then working substance, then Q is equal to U2 minus U1, that is MCV T2 minus T1. Okay, so here these use are lowercase specific quantities, specific volumes, and here I mean specific internal energies, and here this is a normal internal energies. Okay, So observe this difference. Here I have written capital U is equal to mu. Then coming to the next one is reversible constant process or isobaric process. P is equal to constant. Okay. Then here same example you take, but here the piston is a movable piston we are considering. So in the container we have taken a gas and then we are supplying the heat energy to the system gas. Okay, so the gas started expanding, obviously. So pressure rise may be there. Then the piston starts moving. So this is the initial position, final position. The same we can able to represent on the PV diagram. So here the pressure remains constant, okay, but the volume changes. So this is the initial condition of your gas, and after undergoing this particular process, then it has reached to the final condition too. Then this particular process, constant pressure process, which is also called the isobaric process, that we have represented like this. Okay, since it is a heating process, the arrow mark direction towards the right. Okay, so remember, so on the PV diagram, so isobaric process is in a horizontal line. Okay, so now we will see what is a work and what is a heat interaction. And before going for that particular thing, just observe the isobaric process video. Okay, now the beaker we have taken. So the beaker is placed on the stove. Okay, so here this particular volume, inside control volume, is controlled by this particular piston. Here we have a moving piston. It is attached to a pressure gauge and which is fitted with a temperature indicator, thermometer. Okay, so as you supply heat, what is happening? So here the gas started expanding. Obviously, the piston rises up. Okay, so there is a rise of pressure. Okay, and rise of temperature as the piston falling, the pressure increases, and temperature, see temperature also increasing, decreasing. Okay, you observe. So this process is called what? Isobaric process. Okay, then here consider the unit mass of working substance and applying the first law of thermodynamics. Then the work done relation, if you observe, W is equal to integral 1 to 2 PdV, which can be expressed as P of V2 minus V1. Okay, then Q is equal to U2 minus U1 plus P of V2 minus V1. Okay, then separating it and rewriting the P2 V2 minus P1 V1. Then again, so in terms of enthalpy, separate it. Okay, then U2 plus PV2 minus U1 plus PV1, which can be written as H2 minus H1. Okay, then Q is equal to H2 minus H1, which can be written in terms of temperature difference PP T2 minus T1. So this is a work interaction and heat interactions during the isobaric process. Okay, so for mass of M of working substance, Q is equal to mCp T2 minus T1. Then taking the isothermal process. So here isothermal process means temperature remains constant. Whether the inside the system there may be a compression or there may be expansion, but a compression expansion following the isothermal temperature remains constant, then we can say that isothermal process. But in practice, isothermal process may not be possible unless otherwise if you follow the quasi static conditions, quasi equilibrium conditions. Very slowly you have to give momentum to the piston, then the constant temperatures we can able to maintain. Okay, so here in case of a isothermal process, how do you represent on the PV diagram? See here, so which is in a curved fashion. Okay, PV, the governing law is PV is equal to constant. Okay, then here we will just observe what is the work interaction and the heat interaction. Consider the unit mass of working substance, then apply the first law to the process. Q is equal to U2 minus U1 plus W. Then this change of internal energy can be expressed in terms of temperature difference, Cv of T2 minus T1 plus W. Okay, then here in case of isothermal process, T1 is equal to T2, then this becomes 0 plus W, Q is equal to W. Okay, then W is equal to integral 1 to 2 PdV. Then for isothermal process, what is the governing law? PV is equal to constant, P equal to C by V we can write, where C is constant. Then W is equal to integral V1 V2 of C dV by V. Then integrating this and applying the limits, then we can able to write it as C of ln V2 by V1. Then the constant can be neither written as in terms of P1 V1 or P2 V2. Since P1 V1 is equal to P2 V2, it is equal to constant. Then W is equal to P1 V1 ln V2 by V1 per unit mass of working substance. Then W in terms of P2 V2 ln V2 by V1 per unit mass of working substance also we can able to express. Okay. Then Q is equal to W P1 V1 ln V2 by V1. Suppose for mass M of working substance, then Q is equal to P1 capital V1 ln capital V2 by V1. Or else in terms of pressure ratio also we can express Q is equal to P1 V1 ln P1 by P2. Okay, so this relation everybody should remember, V2 by V1 is equal to P1 by P2. Okay, then first law apply to the closed systems, reversible adiabatic process. Okay, reversible adiabatic process can be expressed as PV to the power gamma is equal to constant. So an adiabatic process is one in which no heat is transferred to or from the fluid during the process. Okay, such a process can be reversible or irreversible. So here we are considering the reversible adiabatic non-flow process. So considering the unit mass of working substance and applying the first law to the process, Q is equal to U2 minus U1 plus W. Okay, then heat transfer is zero in case of reversible adiabatic process. Okay, so in case of adiabatic process, what is happening? There is no interaction between the system to the surroundings. Okay, so Q is equal to 0, U2 minus U1 plus W. Then W is equal to U1 minus U2 for any adiabatic process. Okay, then this particular equation is true for whether the process is reversible or not, but in adiabatic expression the work done by the fluid is at the expense of reduction in internal energy of the fluid. Similarly, in adiabatic compression all work done on the fluid, so internal energy of the fluid increases. Okay, then for an adiabatic process to take place, perfect thermal insulation for the system must be available. Then, so this is an adiabatic enclosure. So here isentropic compression and expansion we can able to obtain. Okay, see here. Then the derivation of the law PV to the power gamma is equal to constant. So to obtain the law relating to the P pressure and the specific volume for a reversible adiabatic process, let us consider the non-flow energy equation in the differential form. dq is equal to du plus dw. For a reversible process, dw is equal to pdv. Then dq is equal to substituting that pdv there, du plus pdv is equal to 0. For adiabatic process, q is equal to 0. And also for perfect gas we know that PV is equal to RT or PV is equal to RT by V. Here substituting du plus RT dV by V is equal to 0. Also U is equal to CV of T or du is equal to CV of dt. Okay, then CV dt is equal to RT dV by V. Okay, then dividing both sides by T we get CV of dt by d plus R dV by V is equal to 0, and then integrating we get CV ln t plus R ln V is equal to constant. Then substituting t is equal to PV by R, CV ln PV by R plus R ln V is equal to constant. Dividing throughout both sides by CV, then ln PV by R plus R by CV ln V is equal to constant. Again CV is equal to R by gamma minus 1 or R by CV is equal to gamma minus 1. Specific heat relations we know. Okay, so that using that particular relations and hence substituting ln PV by R plus gamma minus 1 ln V is equal to constant. Okay, then ln PV by R plus ln V to the power gamma minus 1 is equal to constant. Then this can be expressed in this particular manner. Then for ln PV to the power gamma by R is equal to constant we can get. Then PV to the power gamma R is equal to e to the power constant, which is nothing but the constant. Okay, or else we can able to write that PV to the power gamma is equal to constant. Okay, like that we can able to obtain the for a reversible adiabatic process or isentropic process, the governing equation as law as PV to the power gamma is equal to constant. Then expression for work. So the same, the reversible adiabatic process we can able to represent on the PV diagram in this particular fashion. Okay, here the shaded area. See here, the shaded area which gives you the work done. Okay, This area can be evaluated by integration. W is equal to integral v1 to v2 pdv. Okay. Then here we know that pv to the power gamma is equal to constant. Then w is equal to integral v1 v2 c of dv by v to the power gamma. Then integrating that, we get this. And again, the constant in this equation can be written as p1 v1 to the power gamma r p2 v2 to the power gamma. Then substituting and rearranging. Okay, then simplifying, we are getting w is equal to p1 v1 minus p2 v2 divided by gamma minus 1. Okay, so in case of reversible adiabatic process, work done is equal to p1 v1 minus p2 v2 to the power, divided by gamma minus 1. So which can be expressed in terms of a temperature difference also. W is equal to r of T1 minus T2 divided by gamma minus 1. Okay, then this is the relationship between T and V and T and P. So by using equation PV is equal to RT, the relationship between T and V and T and P may be derived as follows. So PV is equal to RT, P is equal to RT by V. So putting this particular value in the equation PV to the power gamma is equal to constant, we get T V to the power gamma minus 1 is equal to constant. Then V is equal to RT by P. Substituting this in PV to the power gamma is equal to constant, we get this particular expression. Then so a reversible adiabatic process for a perfect gas between states 1 and 2, we can able to write, okay, so these many ways. P1 V1 to the power gamma is equal to P2 V2 to the power gamma in terms of pressure volume, in terms of temperature volume we can write in terms of temperature pressure. Okay, so these particular ratios are very very important while doing the problems. Okay, you have to remember this. P2 by P1 is equal to V1 by V2 whole to the power gamma. T2 by T1 is equal to V1 by V2 whole to the power gamma minus 1. T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1. Okay, so any three known properties may be given, one unknown may be given. With the help of these particular relations, unknown may be evaluated. Okay, so the work done in adiabatic process per kg of gas is given by W is equal to U1 minus U2. The gain in internal energy for a perfect gas is given by the equation U2 minus U1 is equal to CV of T2 minus T1, or W is equal to CV of T1 minus T2. Okay, so we know that CV is equal to R divided by gamma minus 1. Okay, substituting, we can get W is equal to R of T1 minus T2 divided by gamma minus 1. Already we have seen this. The same again we have got using the equation PV is equal to RT, W is equal to P1 V1 minus P2 V2 divided by gamma minus 1. So depending upon the data in the problem they have given you, accordingly appropriately you have to select these particular expressions. Okay, then next one is polytropic. Okay, we know that poly is many. Okay, it is found that many processes in practice approximately to a reversible law of form PV to the power n is equal to constant, where n is constant. Okay, both vapors and perfect gases obey this type of law closely in many non-flow processes. So such processes are internally reversible. Then we know that for any reversible process, W is equal to integral PdV. So for a process in PV to the power n is equal to constant, we have P is equal to C divided by V to the power n. Okay, then substituting in place of P, so C by V to the power n, taking C out, okay, and integrating and then here simplifying this particular thing, we are getting the work done is equal to P1 V1 minus P2 V2 divided by n minus 1. In terms of temperature difference, we can express as W is equal to R of T1 minus T2 divided by n minus 1. Okay, then the equation is true for any working substance undergoing a reversible polytropic process. So which follows also that for any polytropic process we can write P2 by P1 is equal to V1 by V2 whole to the power n. Okay, then the following relations can be derived same as for reversible adiabatic process T2 by T1. So temperature ratio in terms of specific volume. Okay, so in terms of pressure ratio, like this we can express. Then heat transfer during the polytropic process. Okay, So using non-flow energy equations, the heat flow or transfer during the process can be found at Q is equal to U2 minus U1 plus W, Cv of T2 minus T1 plus R of T1 minus T2 divided by N minus 1. Then Cv is equal to R divided by gamma minus 1. Substituting, finally we are getting Q is equal to gamma minus N divided by N minus 1 into W. Okay. So, in polytropic process, the index n depends only on the heat and work interactions, okay, quantity during the process. The various processes considered earlier are the special cases for the polytropic processes for a perfect gas. For example, here, as you put n is equal to 0, okay, pv to the power 0 is equal to constant, that is p is equal to constant, isobaric process. Okay, if n is equal to infinity, pv to the power infinity is equal to constant, unless which can be expressed as p to the power 1 by infinity v is equal to constant, that is v is equal to constant, that is a isochoric process. Then when n is equal to 1, PV is equal to constant, that is T is equal to constant. Okay, so isothermal process where n is equal to gamma, PV to the power n is equal, I mean gamma is equal to constant, that is reversible adiabatic. Okay, so all the processes we have represented on common coordinates, pressure and volume here. Okay, the illustration of that particular PV diagram is given in the figure 4.1 is explained here. Okay, so here the number 1 is the initial state of the working fluid, and here A, B, C, D is the final conditions. Okay, so if you follow the cooling process, and here A dash, B dash, C dash, D dash. Okay, these are the different processes if the working fluid undergoes a heating process. Okay, so how in different manner all the processes, okay, whether it is a cooling or heating, how do we represent in a common diagram, we can able to understand here. Okay, so here 1 to state 1 to A, see here horizontal line, so which shows the constant pressure cooling. Okay, and 1 to B isothermal compression, 1 to C isothermal, I mean reversible adiabatic compression, and 1 to D constant volume heating. Then here 1 to A dash constant pressure heating, and 1 to B dash isothermal expansion, 1 to C dash reversible adiabatic expansion, and 1 to D dash constant volume cooling process. Okay, so slowly step by step, just to go through this and try to understand this PV diagram. Okay, then here it may be noted that since gamma is always greater than unity, then process 1 to C, okay, here process 1 to C must lie in between the process 1 to B and 1 to D. Similarly, process 1 to C dash must lie between the processes 1 to B dash and 1 to D dash. Okay, then this is a summary table of all the processes what we have learned in the previous slides. Okay, so constant pressure whose index here, how do you represent, and heat addition, work done, and PVT relations, specific heat. Okay, so these are the summary table of here all processes which is undergoing a closed systems, which is following the closed systems, and these are the problems related to the non-flow processes. Okay, so here again internal energy we are evaluating, and here the amount of heat rejected we are evaluating, and these are the problems related to the non-flow. Some examples we have taken. Okay, so number of problems we have. Okay, so container is divided into two compartments by a partition. The container is completely insulated so that there is no heat transfer. One portion contains gas at temperature T1 and pressure P1, while the other portion also has same gas but temperature T2, pressure P2. How will the first law of thermodynamics conclude the result if partition is removed? Okay, so this is one typical problem. Okay, according to the first law, what is the governing law? Del Q is equal to du plus dw. So when portion partition is removed, okay, since it is a insulated container, del Q is equal to 0, and del W is equal to 0, and du is equal to 0. So this is conservation of internal energy. Okay, So these sort of many problems we have. So this is a problem on non-flow processes. Here we have taken a plant. We have taken calculate the steam flow around the cycle. They have asked you to calculate. So many number of problems we have. Okay. So this already I have shared to you. So in the PDF, just go through that. Okay. See here, this is also one high order thinking problem. A housewife on a warm summer day decides to beat the heat by closing the windows and doors in a kitchen and opening the refrigerator door. At first, she feels cool and refreshed, but after a while, the effect begins to wear off. Evaluate the situation as it relates to the first law of thermodynamics, considering the room, including the refrigerator as a system. Solution. What is the solution here? Okay. So here, initially, the temperature of air in the room falls when it communicates with the cool refrigerator with its door open. So this makes the housewife feel cool. Okay. So here, first of all, what is a system? Room and its contents as a system, and assume the walls, windows, doors non-conducting. In such case, Q is equal to 0. To operate the refrigerator, we must supply the electricity from outside, and hence external work W is done on the system. Applying the first law, Q is equal to delta U plus W, where Q is equal to 0, delta U plus here the work being absorbed, okay, supplied, negative, so minus W, and here delta U is equal to W. Okay, so then we can conclude that the right hand side is a positive figure indicating that increase in internal energy of the system with the time. So as the energy is increasing, the temperature of air also increases, and hence the effect of coolness gradually begins to wear off. Okay, so which may be pointed out here that in this particular case, the energy rise manifests itself in a rise in temperature. Okay, so in the next video lecture, we apply the first law of thermodynamics to the flow processes.